So here we have another optimization problem. This one's kind of interesting. So we've got a power line that needs to be run from a power station here, located on the beach, to an offshore facility over here. Now, the cost to run the power line is $50 to run it along the land. So $50 cost here. Let me do a different color so this will be able to tell the difference here. So $50 along the land here. And then the cost to run it on the water, through the water here, is $130. Okay? So what we're trying to do, anytime you got a business, you want to minimize your overall cost, right? So how much of the power line should be run along the land versus how much of the line should be put into the water, right? So that we minimize the overall cost of running the power from our power station here on the beach to this point right here. So anytime we're talking about an optimization problem, and I know I didn't say this in earlier videos because it kind of didn't really make sense to talk about the extreme cases, but when you think about the extreme value theorem, okay, the extreme value theorem has absolute max or mins at the endpoints or at critical values, right? So not only do we need to check the critical values where the derivative is equal to 0 or where the derivative doesn't exist, but we also need to check those endpoint values there. So I need to define an x. So I've got my beach and I've got the water. And so I've got this 5,000 distance here, okay? Now what's changing is how long this length is right here. Maybe it would be more optimal for us to make the length to right here and then go into the water. Heck, maybe it might be better if we made it right here and then went into the water the rest of the way there, right? It could be the case that the best thing to do is stay along the beach all the way until we're perpendicular with the offshore drilling facility, right? And then we come straight out to minimize our distance in the water, right? But regardless, we need to come up with a distance here, some arbitrary distance. Let's call that distance so that where it splits between going from land to going to water, let's call that distance x, okay? So now if I know that this side is x and the whole thing is 5,000, then to get this other part right here, I need to take 5,000 and subtract x, okay? Because if you think about it, if you add the two parts together, what should you get? You should get the whole thing, right? 5,000 minus x plus x gets me 5,000. I know it's kind of silly, but sometimes it helps if it's written out. Okay? Now, we could minimize the distance as a straight line from the power station to the facility. The only downside to this here, because you might be thinking, okay, Mr. Clark, well, if I'm going to make this like the most minimized cost, I need to minimize that distance, right? The only issue that I have with you minimizing the distance here is the cost difference between running it on the land and then running it under the water. It's more than double the cost to run it underwater. And even though the distance is minimized here, the whole distance is more than double the cost of running it on the land, right? So here, that situation where we would have it all underwater means that I would have this whole distance for my x value. So that would be a scenario where x is equal to 5,000. So 100% of the line would be at the cost of $130. So how can I use math to calculate that? Well, if I set up the Pythagorean theorem here, I know that this side is 5,000 and this side is 1,000. So a squared plus b squared equals c squared, but I don't want c squared, so I take the square root of that number right there. And that is all of the water, all of the line in the water, right? Okay, so if I run through those calculations, I will get a number, and that will be my distance. My distance is 5,099 feet. Okay, so it's 5,099 feet that will all be underwater power line. Okay, now for each foot, I pay $130. So I'm going to take 5,099 and I'm going to multiply it by 130, and it ends up having a cost of 662,872.54. Now, I want you to know that this 5,099 is actually a rounded version of this. I took that number and multiplied by 130, and that's a more exact solution than if I multiplied these two numbers together. Okay, just so you're not wondering, like, well, where did the decimal come from, right? Okay, so that's one extreme value. So the largest that x could be is if the whole thing was in the water, right? What is the smallest that x could be? We could take the value, we could take the shoreline and run it all the way over, 5,000 feet over. And so that would give me an x equal to 0 feet on the shoreline. So x represents how many feet subtracted from 5,000 is on the shore. Okay, so an x equal to 5,000 is 0 feet on the shore, and x equal to 0 is 5,000 feet on the shore. Now, this minimizes the more expensive power line usage. So we go all the way over on the beach, and then what do? We minimize that distance. The minimum distance is that perpendicular distance from your object to where you're heading towards, okay? From where you're heading towards. So that means that there's 5,000 feet on the land, okay? And then what? Then there's 1,000 feet in the water, okay? So what does that look like? So I've got my power source here, and then my offshore drilling well here. I travel 5,000 feet on the land, that's an x equal to 0. And then on perpendicular distance, it's 1,000 feet this way. So I'm going to spend 5,000 feet at a rate of $50, okay? So I'll multiply 50 times 5,000. And then I'm going to spend 1,000 feet, that's where I'm underwater, at a rate of $130. Okay, so 130 times 1,000. Now, mind you this, if I've got this distance from the power breaker to the power source to the oil rig, if I'm traveling this distance here to there, that is the longest distance for the wire, okay? It's the absolute longest distance for the wire. Now, could it be the minimum distance? Maybe so. And maybe this is what somebody who didn't have a math background might say, well, look, we're always trying to minimize cost, so let's just put the most amount of ground wire we can, that's 50, and I picked that because that's the cheapest, right? So we're going to use the cheapest material as long as we can until we get to the point where we absolutely have to use the water material, and then I'm going to use the most expensive part for that shortest amount. And this is the typical solution for what people might do if they're not running a big operation and penny crunch and everything. If you don't maximize profit, without calculus, this would be the easiest way to do it. You would say, look, this is my cheapest amount of power line. This is the most expensive. I'm going to use the cheapest as much as I can. So I'm going to run all the way along the beach. And then, this is the most expensive, so I'm going to minimize that. And the only way to minimize that is to go this distance here, that shortest distance of use. And so that is a solution, right? So if you type this into your calculator, you're going to get $380,000 and say, look how much cheaper this is. It's almost half of what it would cost if we ran the whole thing underwater, right? So somebody might be tempted to say, look, that definitely has to be the minimum cost, right? So the only way to know for sure that this is going to be the minimum cost is to run through it with calculus. So now that we've checked the extreme values, x equal to 0 and x equal to 5,000, we need to run through and form a cost equation and see if there's some critical value between 0 and 5,000 that we can check that might actually have a more minimum cost associated with that x value. Okay? Because maybe it is the case that the optimum solution is to have a little bit some point in between the 5,000 mark where we stop being on land and we go to the water. Okay, maybe it is, maybe it's not. But we're setting up our example here. So I just redrew the picture, and so my cost function is what? Well, if we go back to thinking about it, we're gonna have some fixed cost of money here and some fixed cost of money here. The question becomes, what do we put in for the 5,000 and what do we put in for the 1,000, right? So we already kind of have an idea for this first part of what's on land, okay? This is the distance on land is dependent on x is 5,000 minus x, right? So this is the distance that's on land. It's going to be at the $50 rate. So I do 50 times the 5,000 minus x, okay? And then the second part is the part that's on the water. Well, how do I find that distance on the water? Well, it's the Pythagorean theorem again, okay? So it's a squared plus b squared equals c squared. So I take the square root of a squared plus b squared, okay? And so that is what I plug in for here. That's the amount that's going to be underwater as a function of x. So now I have a cost function set up here. Okay, this cost function works for values of x between 0, what we said here, and 5,000, what we said there. If I get anything over 5,000, I'm going to have a negative number of feet here, and that's no bueno. Okay, and I can't have anything less than 0 because that would mean that I have a negative amount of feet. That makes no sense. So here's my domain for this function here. We've already tested the endpoints for the extreme value theorem, right? So the absolute max or min, the absolute minimum could be an extreme value. So what we've found so far is that if I plug in 0, I get 380,000. If I plug in 5,000, I get 662,000. So before I do any other math, I know that this number is not going to work because this number is lower. Okay, I'm looking for that minimum cost. So let's take this and I'm going to distribute out the 50 times 5,000 is 250,000. And then the 50 times negative x is negative 50x. Then I'm going to distribute this here. I'm just going to rewrite it. I'm going to multiply out 1,000 squared. It happens to be 1,000,000. Okay? So now that I have my cost function, let's take the derivative. The derivative of a constant is 0. The derivative of negative 50x is negative 50. Now, this next derivative, I'm going to pull a constant out front. The derivative here is a chain rule. Okay, to take the derivative of a chain rule, I'm going to rewrite this as x squared plus 1,000,000. Oh my gosh. Raised to the, now the square root can be rewritten as a 1/2. Okay, so this is a chain rule where the inside, I take the derivative of outside, the 1/2 comes out front. X squared plus 1,000,000. Okay, and then I subtract 1 from the exponent. That makes it negative 1/2. But once I take the derivative of the outside, I need to take the derivative of the inside. The derivative of the inside is a 2x plus 0. Okay, so this negative exponent can go to the denominator. So I have a 2x over 2 times x squared plus 1,000,000 to the 1/2. Remember, when we flip this to the denominator, the exponent changes. Okay? Now, once again, you can rewrite this part in here as a square root. What do we see? The 2's actually cancel. Okay? So I'm going to end up having 130 times x over the square root of x squared plus 1,000,000. I set this equal to 0 because to find critical values, I have to set the derivative equal to 0 or where it does not exist. But since this is squared, and then I'm adding a million, there's no way a square can be negative. So the smallest this could be is 0. So the smallest that denominator could be is the square root of a million, which is 1,000. So since this is 1,000 is the smallest it'll ever get, it'll never be dividing by 0. And then here, I don't have to worry about anything because it's just a constant. So there's nowhere that the derivative does not exist, okay? So what I'm going to do is I'm going to solve this equation for x. How do I do that? I'm going to move the 50 to the other side. So I move it to the other side. And now what I'm going to do is I'm going to square everything, okay? So I'm going to square everything. So I have 50 squared over 1 squared times 130 squared times x squared over x squared plus a million. Okay? So I squared everything. Now I want to cross multiply. And if I cross multiply, I'm going to get 50 squared distributed into here gets me 50 squared x squared plus, and I'm going to rewrite this as 10 to the 6th power. That way I don't have to keep writing all those 6 zeros. So that's 50 squared times 10 to the 6th squared. Okay? And that's equal to 50 squared. So let's go through here and see if we can't simplify a bunch of this mess here. Okay? So when I run through all that math, I'm going to get x squared plus 1 million in parentheses times 50 squared, like we squared both of those, cross multiplied, and then 130 squared and x squared times 1, right? So that's what's going on there. So that's where that's coming from. We just squared it and cross multiplied. So what I want to do now is I'm going to distribute to get 50 squared x squared, and then once again what I said, 50 squared times 10 to the 6th. That's just 10 to the 6th right there. Equals this right here. Okay? So what I'm trying to do is I'm going to leave this on that side, and I'm going to move this over to the other side. So I'm going to take this, I'm going to move it over to the other side. To do that, I need to subtract. So I subtract 50 squared x squared, and I notice that both terms have an x squared in them, so I'm going to factor that out. So I have 130 squared x squared minus 50 squared x squared, right? I'm going to factor out the x squared, and that leaves me 130 squared minus 50 squared. That's what I'm doing there, okay? Now, I want to get x by itself, so I need to divide both sides by this nasty number here. So that will cancel there. And so I have x squared equals this nasty thing right here. So I'm going to rewrite this x squared equal to this thing right here. Okay. Now to get x by itself, I'm going to square root both sides. When I square root both sides, the square goes away and the cube turns to... the 6th power turns to the cube power, and that square goes away here. And I take the square root of the denominator. And so you can just type this in your calculator, and you can write this. This is the exact answer, 1250 over 3. Decimal, that's 416.67. If you wanted to be safe, you could put more decimals there, like 6666667, whatever makes you comfortable. This is the exact solution right here. Okay? So you have, technically, when you square root, remember there's a plus or a minus, but a x equal to a negative 416 doesn't really make sense in the context of this problem, since x represents the distance less on the beach. Okay? So the distance of the power line on land is equal to what? Well, the distance of the power line on the land is 5,000 minus x. Okay, so that's what we have written here. Now x, we've said, is the 41667, which is this number here. So I type that in my calculator, I get 4,583 feet. So 4,583. So that means, okay, so that means that 4,583 feet is on the land. So that's really close to being all the way, right? So 4,583 feet on the land. And then we have a slight amount that's on the water. Golly, is that even going to make a difference? Let's see. So the distance of a power line underwater is what? Well, we already determined that. See, this was on the land, right? On the water, though, was this distance here. So that distance is the square root of x squared plus 100 or 1,000 squared. Okay, so the distance under water is this distance here. So I'm going to take my value that I found for my x value and plug that into my distance, and that's going to give me approximately 1,083 feet. Okay, so this is really close to being that straight distance right there, okay, of 1,000, but it's technically a little bit more. All right, so technically it's a little bit more. So it's maybe like at a slight angle because it's 1,083 instead of the exact 1,000. Okay. So if you'll remember, when I had exact 1,000 and exact 5,000, I got 380,000 total. Okay, but now I have like 4,583 right here, and then here I have 1,083. Okay. So what I'm going to do is I'm going to take this x value, the 1250 over 3, and I'm going to plug it into my cost equation. So everywhere I see an x, I'm going to put that 1250 over 3 value in there and see what the actual cost output is. So if I plug that in everywhere, then I get a lot of math, gets me 370,057 cents. How about that? What does that tell me? Well, look at these numbers, people. This number, 370,000, is lower than that 380,000, and it's definitely lower than that 662,000. So what have we done? By being a little bit sneakier, what we've done is we've minimized our cost. Okay, so like drawing a picture of the different scenarios. So let me kind of illustrate this. Okay, so here's our power source, and here's the beach line. Okay. So there's 1,000 feet this way. Okay, let me actually delete this. All right, I'm just going to copy this, and I'm going to have 3 scenarios duplicated just like this to show you the 3 scenarios we got going on here. Okay. So the first one was we were all underwater. Okay, and so we took a power line straight there, and that power line was all underwater. In that scenario, we had 662,000, right? okay? The next scenario was we were on the beach as long as we could be on the beach, and then we were minimizing the amount of distance between the beach and the offshore rig, and that was 1,000 feet here and 5,000 feet on the beach. Okay, so this was the longest distance. That we considered. However, the cost here, the total cost was $380,000. Okay, which might have been surprising that the longest distance was less cost than this. But if you start thinking about it, remember, it's $130 per foot here versus on the beach. Remember, this was like $50 per foot. Okay, whereas here was your 130 per foot. Okay. Now, the difference in our last scenario was, instead of going all the way over, what we did was we went a distance of 4,583.33 feet, okay? And then we took an angle approach to the offshore drilling rig, and we traveled 1,083.33 feet. Okay, and then doing this, my friends, saved us some money. It saved us, so it ended up being 370,000 and then some change, right? So 57 cents. So what does that amount to? That's about $10,000 cheaper than the common sense way that most people would do it. And think about this. Whoa, that is like way cheaper than like if somebody was like, well, let's just do it the shortest distance, right? So if you thought about it more than 5 seconds, you might think that this is the way to go. But it turned out that you actually saved $10,000 if you use calculus here. Now, you might be thinking, well, Mr. Clark, it's $10,000. We're a big company. But say instead of just being one offshore drilling rig that needs power sent out to it, say instead, you've got 10,000 drilling rigs, which for a huge company, maybe that's the case. Well, you're talking about, or maybe let's not even get that crazy. Let's just say there's 1,000 drilling rigs, right? And so you've got $10,000 in savings for each of these rigs for this company. Now, what are you talking about? You're talking about 1, 2, 3, 1, 2, 3, 4. You've just saved this company $10 million. This one decision that you've just made for that company has now saved them $10 million. And you think about that, like say you get paid $100,000 a year, okay, 1, 2, 3, 4, 5. You've just paid for 100 years, justified 100 years of being employed by this company. All right, so this is why math pays. Okay, so you may not think it's that big of a deal for one drilling rig, and maybe if you're a small operation and you've only got 2 or 3 rigs, you don't have to use calculus to find that shortest distance. You just say, look, we know it's cheaper for this, so we're going to maximize this and minimize that, right? That would be like the minimum level, right? You do this route, you're probably not going to be in business that long, especially if you have, more than 1 or 2 drilling rigs. But you talk about the big boys. The only way you can compete with the big boys is if you know calculus. And that's the difference. They have teams of analysts that just go out and they try to figure out how to minimize their costs. Okay. Now, do they use calculus all the time to minimize their costs? Absolutely not. They've got computer programs that a programmer who used calculus actually inputted these values into proprietary software that is in-house computer programming. And so, but somebody at some point had to use the calculus to develop those programs. And if you're going to make new programs in the future, you've got to know calculus to input into those new programs. So just an exciting example where you can actually see where this might actually get used. You're going off to be an engineer or something. Okay, a petroleum engineer or whatever.